In 1959, a Soviet astronomer wrote one sentence in his notebook that the scientific community would spend the next 65 years trying to explain. The sentence was this: Phobos is hollow. And if it is hollow, it is not natural. He underlined it once, he put the pencil down, and the puzzle he created that night has not been fully solved to this day. Moscow, late 1959. The office of Iosif Shklovsky. He is one of the most respected radio astronomers in the Soviet Union, a senior figure at the Sternberg Astronomical Institute. And tonight, he is alone with a problem he cannot resolve. In front of him are years of orbital tracking data, years of measurements of a single object, a small moon, roughly the size of a city, orbiting Mars closer than any natural satellite has ever been observed to orbit any planet anywhere in our solar system. Its name is Phobos, Greek for fear. Shklovsky picks up his pencil. He is checking a number for the third time tonight. The number refuses to change. Phobos is accelerating, not slowing, not drifting, accelerating. The orbit is tightening. The moon is falling toward Mars, slowly, by a tiny fraction each year, but it is falling. That, by itself, is not impossible. Tidal forces can do this. Atmospheric drag can do this. There are explanations, but the rate is wrong. He runs the calculation again. He works backward. To make the math close, to make the orbital acceleration match what the tracking data is telling him, Phobos has to be light, not just a little light, extraordinarily light. He stares at his result for a long time. A piece of rock, the size of a city, 22 kilometers across, orbiting Mars for billions of years, made of material that looks like ordinary asteroid rock, should not be this light. It should be more than twice as heavy, at minimum. Shklovsky is not a man who panics at numbers. He is a senior figure in a serious institute. He has explanations ready in his head before the calculation is finished. The first one, atmospheric drag at high altitude, requires Phobos to be impossibly light. The arithmetic does not work. The second, solar radiation pressure, produces the wrong magnitude entirely. The third, tidal interactions with Mars, explains part of the acceleration, but not all of it. He has now run out of normal answers, so he writes a fourth. He writes one sentence in his notebook. A sentence that, when his analysis reaches the West the following year, will travel from Moscow to Washington and back, and will not be quietly forgotten by anyone who reads it. The sentence is this: Phobos is hollow, and if it is hollow, it is not natural. He underlines it once. He puts the pencil down. Shklovsky was not a fringe thinker. He was not a writer of speculative books or a chaser of headlines. He was the senior figure in Soviet radio astronomy, one of the most disciplined scientific minds of his generation. He had perfectly reasonable explanations ready for what he was seeing in the data. The data refused all of them. So, he proposed something else, and spent the rest of his life being half right, in ways no one fully understood until the next century. This video is about Phobos. It is the inner of Mars' two moons, about 22 kilometers across at its widest point. Heavily cratered, irregularly shaped, like a potato carved by a sculptor who lost interest halfway through. It orbits Mars at just 6,000 kilometers above the surface, closer than any moon to any planet anywhere in our solar system. If you stood on the surface of Mars on a clear afternoon, you would see Phobos rise in the west and set in the east. Twice a day, you would watch it move across the sky in real time, the way you watch a slow airplane. That is not the strange thing about Phobos. The strange thing about Phobos is what is inside it, or rather, what isn't. Across more than half a century, multiple measurements, taken by different programs, across different decades, have returned the same impossible number. Soviet orbital tracking in the 1950s, the Phobos 2 spacecraft in 1989, the European Mars Express probe in 2010, they all agree. Phobos is roughly 25 to 45% empty space. For an object of its size, sitting where it sits, made of what we believed it was made of, that should not be possible. This is not a video about ancient aliens. It is not about secret programs or hidden truths. This is about a single measurement that has refused to resolve for more than 6 decades, and what happens to a piece of science when reality keeps quietly disagreeing with the textbooks. Because here is the heart of it. This is not just about a moon. This is about the one measurement, repeated, confirmed, refined across 3 missions, that made serious scientists stop calling Phobos a normal captured asteroid. And once that measurement settled, everything we thought we knew about the small bodies of our solar system came under quiet, uncomfortable pressure. By the end of this video, you will understand exactly why this number is impossible. You will understand what every credible scientific explanation has tried to say about it, and where each of those explanations breaks down. You will understand why one of the most respected astronomers of the 20th century, looking at the same data we are about to look at, proposed something so strange that the West dismissed it publicly and engaged with it privately for years. And you will understand why, in a way no one could have predicted in 1959, he turned out to be partly right. Just not in the way he thought. So what is actually inside Phobos? Why does every gravity measurement we have ever taken of it return a density that physics says shouldn't exist for a body this size? In this orbit, why did a senior Soviet astronomer publicly suggest, in 1959, that this moon was artificial, and why did Western scientists like Carl Sagan engage with the question instead of dismissing it outright? What happened to the Phobos 2 spacecraft in its final hours before reaching the surface? If Phobos isn't hollow, what is it? And if it is, what put it that way? This is not a textbook lecture. This is not clickbait speculation. This is a real measurement problem, taken from real spacecraft data, examined the way the original scientists examined it, slowly, carefully, with the mystery preserved exactly as it sits in the technical literature. Some of what we will discuss is settled, some is still open, and some of it sits in a strange middle ground that the headlines have never quite captured, where the official answer is not wrong, but it is not quite complete either. Stay, because, by the end of this, the question of what Phobos actually is may not be as resolved as you have been told. Quick pause. If you're enjoying this kind of slow, careful storytelling, hit subscribe. Galaxy Pulse goes deep on mysteries others rush through. Now, back to Phobos. To understand why a single density number created a 6-decade scientific puzzle, we need to go back further than S.H. Shklovsky. We need to understand what Phobos was supposed to be, what scientists in the 1800s thought they were looking at when they first found it, and how the picture began to shift the moment we got close enough to actually measure the thing instead of just observing it from millions of kilometers away. Because the strangest part of this story isn't what we discovered recently. The strangest part is how long the inconsistencies have been sitting there in plain view, in published papers, in mission data, in Soviet observatory logs, waiting for someone to take them seriously enough to ask the obvious question: what is this thing? The story of Phobos begins on the 18th of August, 1877. Iosif Hall, an American astronomer working at the United States Naval Observatory in Washington, was searching for moons of Mars. The search had not been going well. Several nights of careful observation had produced nothing. By his own admission, he had nearly given up. His wife, Angeline, talked him into trying one more night. That night, he found Deimos. 6 nights later, he found Phobos. He named them after the sons of Ares, the Greek god of war, equivalent to the Roman Mars. Phobos, meaning fear, Deimos, meaning dread, the chariot horses of war in mythology. It was the kind of literary touch that 19th century astronomers permitted themselves when they had time to think. For the next 90 years, Phobos was little more than a faint dot in a telescope. Astronomers measured its orbit, they calculated its rough size, they estimated its brightness. They placed it, comfortably, in a category that already existed, a captured asteroid. The standard story went something like this. Billions of years ago, a chunk of primitive rock, probably from the outer asteroid belt, or possibly from beyond it, drifted too close to Mars. The planet's gravity caught it. The orbit stabilized, and there it has been, falling slowly toward Mars, ever since. It was a tidy story, it fit. There were similar bodies elsewhere in the solar system, irregular, small, dark moons that looked like asteroids and probably were asteroids, just ones that happened to live near a planet now. Phobos was treated as a kind of free sample. A piece of the asteroid belt parked conveniently in Mars orbit, ready to be studied without sending a mission to the asteroid belt itself. Every textbook on planetary science from the early 20th century onward described it the same way. Captured, primitive, unremarkable in composition, distinguished mainly by its odd orbital speed and its strange surface grooves. Here is the surprising part. If you stood on the surface of Mars and looked up at Phobos, it would not look like our moon. It would look like a fast, dark stone, roughly 1/3 the apparent size of Earth's full moon as seen from Earth, but it would be moving, visibly moving, across the Martian sky, in real time. You would see it complete an entire pass in roughly 4.5 hours, rising in the west and setting in the east, backwards from every other moon humans have ever observed from a planet's surface. You could literally watch it travel. That is how close Phobos is to Mars. It orbits at 6,000 kilometers above the Martian surface. By comparison, our moon sits 384,000 kilometers above Earth. Phobos is 60 times closer to its planet than our moon is to ours. That closeness will become important. Hold on to it. For now, the picture in everyone's head, going into the middle of the 20th century, was this. Phobos was a captured asteroid, a chunk of dark, primitive rock. It looked like an asteroid, it behaved, mostly, like an asteroid, and there was no reason to think it was anything else. Then somebody decided to actually measure it carefully. Here is what we should have seen. A captured asteroid, the size of Phobos, made of the kind of dark, carbon-rich material we believed it was made of, what planetary scientists call carbonaceous chondrite. The same broad family as many asteroids we have since visited directly, should have a density somewhere between 2.2 and 3 grams per cubic centimeter. That is the density of solid rock, the density of asphalt, the density of the chunk of basalt you might pick up off a hiking trail. This is not a guess. We know what asteroids are made of. We have visited several with spacecraft. We have brought samples back to Earth. The math is well established. A chunk of rock, the size of Phobos, made of the material it appears to be made of, should weigh about what a chunk of rock that size should weigh. That is not what Phobos weighs. Every modern measurement of Phobos returns a density of approximately 1.86 grams per cubic centimeter. The difference, on paper, sounds modest, 2.5 versus 1.86. Not even a factor of 2, but in planetary science, this gap is enormous. Density is not a small number. Density is the most direct measurement we have of what an object is made of. Density tells us, almost more than anything else, what the inside of a body looks like. And when the density of an object is 25 to 45% lower than it should be, when there is that much missing mass in a body whose outside looks completely normal, only 3 things can possibly be true. Either the body is made of something much lighter than we think, or the body has enormous empty spaces inside, or the body is not what we think it is. Picture two boxes the same size. One filled with sand, one filled with packing peanuts. From the outside, the boxes are identical. The instant you lift them, you know something is different. That is the situation with Phobos. From the outside, it looks like an asteroid. It is colored like an asteroid. It is shaped like an asteroid. It has craters like an asteroid. But every time we have weighed it, and we have waited across more than half a century, with multiple spacecraft, the number that comes back tells us the box is full of packing peanuts, when it should be full of sand. The first crack in the picture did not appear as a question about density. It appeared as a question about motion. Through the late 1940s and into the 1950s, astronomers were tracking Phobos with patient, methodical attention. They were not looking for anomalies. They were just measuring its orbit, year after year, building a precise record of its motion, and the orbit was changing. Phobos was speeding up, not by much, by a tiny fraction each year, but consistently, in the same direction, year after year, decade after decade. The orbit was tightening. The moon was, very slowly, falling toward Mars. This, on its own, was not shocking. Astronomers already knew that close-orbiting moons can experience tidal forces from their parent planets. They knew that atmospheric drag, even at high altitude, could affect orbits over long timescales. There were normal explanations. The problem was the rate. The acceleration was too fast. Atmospheric drag could explain it, but only if Phobos was significantly less dense than anyone had assumed. Shklovsky ran that calculation. To match the observed acceleration through atmospheric drag alone, Phobos would have to have a density close to that of water, for a moon, made of rock, in space. That answer was so absurd that Shklovsky did not initially propose it as a serious physical conclusion. He proposed it as a way of showing how badly the standard model of Phobos was failing. If atmospheric drag is the answer, then Phobos is impossibly light. Therefore, atmospheric drag is probably not the only answer. He tried other explanations: solar radiation pressure, wrong magnitude, tidal interactions, real but insufficient, combined effects, closer but still leaving a gap. After running through every conventional possibility he could think of, he was left with a residual acceleration he could not account for. The simplest mathematical fit for that residual was a density much lower than rock. So he wrote, carefully, in the language of a scientist, proposing the most extreme hypothesis as a last resort. Phobos may be hollow, and, if it is hollow, the most parsimonious explanation is that it is artificial. He did not say it was alien. He did not invoke conspiracy. He proposed it as the residual that survived after every conventional explanation had been ruled out, and he proposed it knowing exactly how strange it would sound. The Western response, at first, was dismissal, Soviet speculation, Cold War mysticism, not a serious idea. The Western response, in private, was different. Carl Sagan, in the early 1960s, engaged with Shklovsky's calculation directly. He did not endorse the artificial moon conclusion. He was clear about that. But he treated the underlying density problem as a real puzzle. And he and Shklovsky later collaborated on a major book about extraterrestrial life that grew partly out of these conversations. The first attempt to dismiss the puzzle was simple. The orbital acceleration measurement must be wrong. Eventually, by the late 1960s, improved measurements showed that the original drag-based calculation had overstated the problem. The acceleration was real, but smaller than first reported. Some of Shklovsky's numerical urgency disappeared. The density problem, however, did not go away, it just moved. As measurements of Phobos's actual mass and volume improved over the decades, the gap between what Phobos weighed and what a normal asteroid of that size should weigh became clearer, not smaller. The hypothesis space narrowed. The body was not made of standard rock, or it was not solid, or it was not what we said it was. By the time S.H. Shklovsky died in 1985, the density problem had been sitting in the scientific literature for a quarter century. It had not been solved. It had not been explained away. It had simply been waiting for somebody to fly a spacecraft close enough to settle it directly. 4 years later, somebody tried. Before we go to that mission, let's slow down and make sure the science here is clear. Because the entire story rests on understanding a few things, and they are not difficult, they have just been obscured by jargon for decades. The first question: how do we measure the density of something we have never landed on? The answer is gravity. Every object with mass exerts a gravitational pull on everything around it. When a spacecraft flies past a moon, the moon's gravity tugs on the spacecraft. The harder the tug, the more mass the moon has. By tracking how the spacecraft's path bends, by measuring the tiny shifts in its radio signal as it passes, we can calculate, very precisely, how much mass the moon contains. We can also measure its volume directly, by photographing it from multiple angles. Volume is just how much space it takes up. Mass divided by volume equals density. That is the whole calculation. This is not an exotic measurement. It is one of the most reliable measurements in planetary science. We do it every time a spacecraft flies past a body. The numbers we get are good, usually accurate to within a few percent. So when we say Phobos has a density of 1.86 grams per cubic centimeter, we are not guessing. We are not extrapolating. We are reporting a measurement. The second question: why is that number a problem? Because we know what the inside of a captured carbonaceous asteroid should look like. We have visited several. We have brought samples back. They are dark, dense rock. They are not water. They are not foam. They are rock. A solid body of that material, the size of Phobos, would weigh a specific amount. Phobos weighs significantly less than that, which means a significant fraction of the inside of Phobos, by volume, is not there. This is not surface porosity. That is the small holes you would find in a piece of pumice. Surface porosity can account for maybe 10% of a small body's volume at the high end. It cannot account for what we measure here. We are talking about macroporosity, large-scale internal voids, cavities, empty space, deep inside the body, in chunks big enough that they affect the overall weight of the moon by a significant fraction. Depending on what assumptions you make about the material Phobos is built from, that empty fraction could be anywhere from 15%, if the moon is built from light, primitive chondrite-like rock, to 45%, if it is built from something closer to ordinary Mars-like rock. That is what the data is telling us. That is what the data has been telling us, consistently, for over half a century. So here is where the stakes start to rise. If the density measurement is correct, and it has been confirmed by progressively better instruments across more than 6 decades, then Phobos is not what we said it was. And if Phobos is not what we said it was, then our entire framework for understanding small captured bodies in the solar system needs revision. Suddenly, this isn't a small anomaly anymore. This is a question about how moons form, about how asteroids get captured, about whether the simple, comfortable picture of small irregular moon equals captured asteroid applies to other places we have not bothered to verify carefully. What about Deimos, Phobos' smaller, outer companion? We have measured its density less precisely. Could it be hiding something similar? What about Hyperion, Saturn's strange sponge-like moon, with a density even lower than Phobos? What about Nereid, Neptune's irregular outer moon? What about the dozens of small captured bodies we have catalogued but barely studied? If one of them is wrong, others might be too, and there is a more practical question. Phobos has been proposed, more than once, as a potential staging base for human Mars missions. It is close. It is low gravity. It would be cheaper to land on than Mars itself. If we are going to send astronauts there in the next few decades, we need to know what is actually inside the thing they are going to be standing on. Is it solid? Is it a rubble pile that could collapse under their feet? Is it riddled with internal cavities that might offer natural radiation shelter, or that might have shifted and reformed during impacts in ways that make the surface unstable? We do not know. After more than 60 years of measurement, we still do not know everything we need to know. And the open question that will not go away, the one S.H. Shklovsky stated bluntly in 1959, and that nobody has fully buried since, is this one. If Phobos is hollow, what made it that way? If the orbital acceleration had been the only strange thing about Phobos, the story might have ended in the 1960s. A footnote in a textbook. An interesting measurement, eventually explained away by better data, better models, better understanding. It was not the only strange thing, because in 1989, the Soviet Union sent a spacecraft to investigate this moon directly. It was called Phobos 2. It was the most ambitious robotic mission to a Martian moon ever attempted. It was supposed to fly close, deploy landers, and return data that would settle the density question once and for all. It got close. It got data. And then, in its final hours before close approach, moments before it would have made the closest measurements any spacecraft had ever made of Phobos, something happened. The mission failed. The spacecraft went silent. What it had returned up to that point only deepened the puzzle. The year is 1988. The Soviet space program is in the final years of its existence, though no one quite knows that yet. Money is tight. Political pressure is heavy. The Cold War space race has been over, technically, for more than a decade. But the Soviet Union has decided to do something the Americans have not done. It has decided to send a spacecraft directly to Phobos, not a flyby, not a distant photograph. A close-approach mission designed to study the moon in detail, deploy small landers onto its surface, and finally, answer the question that had been sitting in the literature since S.H. Shklovsky first wrote it down. What is inside this thing? The mission consisted of two spacecraft, Phobos 1, Phobos 2. Phobos 1 was launched on the 7th of July 1988. It was lost about 2 months into its journey before reaching Mars. The cause was not exotic. A flight controller on Earth had transmitted a command sequence that contained a single-character error. The error invoked a test routine, one that had been left in the spacecraft's permanent memory because removing it before launch was deemed too risky to the schedule. That routine deactivated the spacecraft's attitude control thrusters. It did exactly what it was told. It tumbled. It lost its solar panel orientation. It died in silence on the way to Mars. Phobos 2 carried the weight of the entire program from that moment onward. It launched on the 12th of July 1988, 5 days after Phobos 1. It made the long crossing without incident. On the 29th of January 1989, it entered Mars orbit successfully, one of only a handful of spacecraft to do so up to that point. It began a series of preliminary observations. The instruments worked, data flowed back to Earth. Soviet scientists began to plan the close approach phase. That phase was supposed to begin in late March. The plan was straightforward in concept and terrifying in execution. Phobos 2 would slowly maneuver itself to within 50 meters of the moon's surface. From that distance, it would deploy 2 small landers, one stationary, one a mobile, hopper, and conduct close-range gravity measurements that would, for the first time, map the interior structure of Phobos directly. If the moon was a solid body, the gravity field would be smooth and predictable. If it had internal voids, the gravity field would be lumpy. The data would tell us which was true, definitively, for the first time in 30 years. Before that close approach, Phobos 2 had already returned data that strengthened the case Shklovsky had been making since the late 1950s. Thermal measurements suggested that Phobos was retaining heat in patterns that did not look uniform. Some regions of the surface cooled differently from others, more than scientists had expected for a single, solid lump of rock. The thermal map of Phobos, in other words, was harder to reconcile with a simple, uniform body than with one that had an irregular interior structure. The gravity measurements taken during the orbital phase, before close approach, were consistent with the density anomaly. They reinforced what Earth-based observations had been suggesting all along. The number was holding. On the 26th of March 1989, Phobos 2 began its final maneuver toward close approach. On the 27th of March, contact was lost. The spacecraft did not respond to the next scheduled communication window. Soviet ground teams worked to re-establish signal. They got nothing, except, at one point, a brief, weak transmission they could not lock onto. They tried again over the following days, nothing more. Within a week, the mission was officially declared lost. The official cause, as determined by the Soviet investigation, was a malfunction of the onboard computer, which led to an attitude control failure. The spacecraft drifted off-axis. Its high-gain antenna stopped pointing at Earth. Its solar panels stopped pointing at the sun. By the time anyone could intervene, the batteries had drained and the spacecraft had gone permanently silent. That is the official explanation. It is the most likely explanation. It is consistent with the engineering data Phobos 2 transmitted in the hours before it failed. Phobos 2 never reached the surface. Whatever it was about to measure, in those final 50 meters, was not measured. And the data it had returned up to that point told the same story Shklovsky had been telling for 30 years. The numbers did not fit a solid moon. The thermal behavior was awkward to explain. Something inside this body was not what the textbooks said it should be. If Phobos 2 had been the last word on this, we would still have an unexplained mission failure and a confirmed density problem. But it was not the last word. 20 years later, a European spacecraft would do what the Soviets could not. It would fly close enough to settle the gravity question with modern instruments. Instruments far better than anything Phobos 2 had carried, operating in an era when the data could be cross-checked across multiple agencies and verified beyond any reasonable doubt. And the answer it returned was, somehow, even stranger than what came before. Mars Express launched in June of 2003. It was the European Space Agency's first independent mission to another planet. It carried a suite of instruments designed to study Mars from orbit: high-resolution cameras, atmospheric sounders, ground-penetrating radar, magnetometers. It was not, originally, designed as a Phobos mission. Phobos was a target of opportunity, but Mars Express's orbit, by design, brought it close to Phobos on a regular schedule. Several times a year, the spacecraft would pass within a few hundred kilometers of the Moon. Each pass produced data. Each pass refined the gravity measurement. Then, European mission planners decided to do something unprecedented. They would lower the closest approach to Phobos to less than 100 kilometers. Then less than 70. Eventually, on the 3rd of March 2010, they brought Mars Express to within 67 kilometers of the Moon's surface. That was the closest any spacecraft had ever flown to Phobos. It was, in pure measurement terms, the moment the question was finally settled, at least at the level of bulk density. Here is how the measurement worked. As Mars Express flew past Phobos, the Moon's gravity tugged on the spacecraft. That tug shifted the spacecraft's velocity very slightly. The shift in velocity changed the frequency of the radio signal Mars Express was transmitting back to Earth. The kind of frequency shift you hear when an ambulance siren rises and falls in pitch as it drives past you. By measuring the precise shift in radio frequency, mission scientists could calculate the precise change in the spacecraft's velocity. From that velocity change, they could calculate the precise mass of Phobos. The technique is called Doppler tracking. It is one of the oldest and most reliable methods in deep space navigation. It does not depend on assumptions. It does not require photographs. It just measures how a spacecraft moves when something pulls on it. The result was published, peer-reviewed, in the years that followed. The data was open. The conclusion was clear. Phobos has a density of approximately 1.86 grams per cubic centimeter. The mass was measured 100 times more accurately than ever before. And depending on what you assumed Phobos was made of, the empty fraction of its interior was somewhere between 15% for a body made of light, primitive chondrite-like material, and 45% if the moon was made of something closer to Mars-like rock. Either way, the picture was the same. Phobos was, by a huge fraction of its volume, not solid. The number that S.H. Shklovsky had calculated indirectly, that earlier observations had pointed toward, that Phobos 2 had supported in part, was now confirmed by modern European instruments operating with precision the earlier missions could not match. The density problem was real. It was no longer in dispute. The next question, of course, was what to do with that result, and here the scientific community had to make a choice. They could stand on the data, confirm the anomaly, declare Phobos to be a body that did not fit the standard captured asteroid model, and begin the long work of figuring out what kind of body it actually was. Or they could find an explanation within the existing framework that accommodated the density without requiring Phobos to be anything truly unusual. They chose the second path, and the explanation they reached for was the rubble pile. A rubble pile is exactly what it sounds like. It is a body that is not a single solid rock, but a loose collection of smaller rocks held together by their mutual gravity. There are real rubble piles in the solar system. We have visited them. The asteroid Bennu, which the OSIRIS-REx mission studied in detail and from which it returned samples to Earth, is a confirmed rubble pile. So is the asteroid Itokawa, visited by the Japanese Hayabusa mission. Comet 67P, the target of the European Rosetta mission, has rubble pile characteristics in its nucleus. Rubble piles are real. They have low densities, because the gaps between the rocks count as empty space when you measure overall density. A rubble pile asteroid can have a density of around 1.5 to 2 grams per cubic centimeter, comfortably in the range Phobos shows. So the explanation was straightforward. On paper, Phobos is a rubble pile. The empty space is the gaps between the rocks. Mystery solved, except it was not quite that simple, because the rubble pile theory has known mismatches with the rest of the Phobos data. Mismatches that exist in the technical papers, but rarely make it into public coverage. The first mismatch is structural. Phobos orbits Mars at 6,000 kilometers. That is extraordinarily close. So close that tidal forces from Mars are pulling on Phobos all the time. A rubble pile, sitting in that kind of gravitational stress, should not survive easily over the long term. The rocks should drift apart. The body should disaggregate over geological timescales. The fact that Phobos has held together for billions of years in this orbit suggests something more cohesive than a loose pile. The second mismatch is the grooves. Phobos has long, parallel furrows running across its surface. We will return to those grooves in detail in a moment. For now, the relevant point is that the groove patterns do not all match what we would expect from a pure rubble pile. They match better what we would expect from a body with at least some internal coherence, something more like fractured solid rock, with stress lines, than a heap of loose stones. The third mismatch is the thermal behavior. As we discussed earlier, the way Phobos' surface heats up and cools down does not look entirely uniform. It looks more like a body with internal complexity, voids, cavities, regions of differing density, not a uniform mix of rocks. So the rubble pile theory fits the density. It does not fit the structure as cleanly. It does not fully account for the surface features. It does not fully account for the thermal data. It is, in the language scientists actually use when they are being careful, a partial fit. In the language scientists use when they are not being careful, it is just the answer. Some researchers argued that rubble pile was the natural answer, that small bodies of this kind almost always have internal voids from gravitational accretion, and the other anomalies could be explained by additional factors. Others pointed at the data and said, a rubble pile, this close to Mars, this old, with these specific groove patterns, does not quite work. The fit is good, it is just not perfect. And, in planetary science, not quite perfect is where the interesting questions lie. The 2010 result, in other words, did not close the case. It opened a new chapter. The density anomaly was real. The simple explanation was incomplete. And the closer scientists looked at Phobos in the years after, the more they began to see features that no single existing theory could account for. Look closely at any high-resolution image of Phobos, and you will see them. Long, parallel lines running across the surface, like someone took a comb and dragged it across the moon. They are grooves, actual physical furrows in the surface, and they are one of the most distinctive and least understood features of the entire body. The largest grooves are around 100 to 200 meters wide and tens of meters deep, running for distances comparable to Phobos' own diameter. They run in roughly parallel sets. They are concentrated, but not uniformly distributed, and the pattern of their distribution has fascinated scientists since they were first photographed clearly by the Viking missions in the late 1970s. What are they? 3 explanations have dominated the literature, and not one of them fully fits. The first explanation is impact debris from Stickney crater. Stickney is the enormous crater that dominates one face of Phobos, about 10 kilometers across, on a body 22 kilometers wide. The impact that created Stickney was the most violent event in Phobos' history. Some scientists have argued that the grooves are chains of secondary impact craters from material thrown up by the Stickney event, which then fell back onto Phobos in roughly aligned trajectories. The problem is that the groove pattern, when mapped carefully, does not radiate symmetrically from Stickney. Some grooves do, others run in directions that have no clear relationship to the crater. And the depths and widths of the grooves vary in ways that are hard to explain through impact debris alone. The second explanation is tidal stress. Mars is pulling on Phobos constantly. The tidal forces flex the moon. Some researchers have proposed that the grooves are stress fractures, long, parallel cracks where the surface failed under repeated tidal flexing. The problem is that tidal stress should produce a specific pattern of cracks, oriented in predictable directions relative to Mars. The actual grooves do not consistently match that prediction. The third explanation is rolling boulders. In the low gravity of Phobos, large boulders thrown up by impacts could potentially roll across the surface for long distances, leaving parallel tracks behind them. There is some evidence for this, but it cannot account for the deepest, widest grooves, which are too large to be explained by rolling debris. Each theory explains some grooves, none of them explains all the grooves. And then, there is Stickney crater itself. The impact that formed Stickney should have destroyed Phobos. Let that statement sit for a moment. A crater, roughly 10 kilometers across, on a moon 22 kilometers across. The impact energy required to excavate a crater of that size, in a body of that size, is at the upper limit of what the body could survive. A solid rock Phobos would have shattered. A pure rubble pile Phobos would have been blown apart and reaccreted into something with a completely different surface. And the modern surface would not preserve the original groove patterns and crater chronologies that we see. What we see, instead, is something stranger, a body that absorbed a near-fatal impact, survived, retained its overall shape, preserved its surface features in ways that tell us the impact did not fundamentally rebuild the moon, and carried that scar, Stickney, for the next several billion years. That is not the behavior of a loose rubble pile. It is also not quite the behavior of a solid rock body, which would have fragmented. It is the behavior of something in between, something with enough internal coherence to hold together, with enough internal void space to absorb shock without flying apart, with a structure, in other words, that does not fit any clean category we currently have. We are starting to see the shape of the problem. It is not just one anomaly. It is a pattern. The density is wrong for a solid asteroid. The thermal behavior is awkward for a uniform rubble pile. The groove patterns are wrong for any single explanation. The Stickney impact survival is wrong for both solid and pure rubble pile models. The orbital acceleration, the original mystery, has never been fully accounted for by any single mechanism. Each of these features, on its own, can be explained away with enough effort. Together, they suggest that Phobos is something we do not yet have a clean category for. And here is where the wider context becomes important. Because Phobos is not the only body in the solar system whose density does not add up. Saturn's moon Hyperion has a density of approximately 0.55 grams per cubic centimeter, far lower than Phobos. Hyperion is so porous that it has been informally called the sponge moon. Its surface is unlike anything else in the solar system, covered in deep, sharp-edged pits that look like the holes in a kitchen sponge. The mechanism that produced Hyperion's structure is still debated. Comet 67P, studied in detail by the Rosetta mission, also showed unexpectedly low density and complex internal structure. The body appears to be made of two lobes joined together, with significant internal voids in both. Asteroid Bennu, studied by OSIRIS-REx, is a confirmed rubble pile, but its surface behavior was so unusual that the spacecraft itself nearly sank into the loose material when it touched down to collect samples. These bodies are not all the same, they are not all hollow, but they share something. They are small, they are irregular, and they all turned out to be more complex, more porous, and stranger than the textbook categories predicted before we visited them directly. Phobos sits within this wider pattern. It is part of a growing realization in planetary science that small bodies are not simple. The neat division between captured asteroid and primitive remnant and rubble pile is breaking down. The reality, when we look closely, is that small bodies have histories. They have internal structures. They have features that emerge from billions of years of impacts, gravitational stress, thermal cycling, and processes we are still in the early stages of understanding. And that brings us to the upcoming Japanese mission. The one that will, finally, settle some of these questions directly. But before we get there, we need to face the fact that there is one more possibility on the table. A possibility that scientific papers have started to take seriously in recent years, but that public coverage rarely discusses. What if Phobos was never a captured asteroid in the first place? There are three serious explanations currently on the table for what Phobos actually is. They sit on a ladder, conservative at the bottom, bold at the top. Each one explains some of the data. None of them explains all of it, and the scientific community is, slowly, starting to climb the ladder. The conservative explanation is the rubble pile. We have already covered this. It is the mainstream view. It accounts for the density. It is consistent with what we have seen on other small bodies. Most introductory planetary science textbooks today describe Phobos this way. Its supporting evidence is the density measurement, the presence of macroporosity in similar bodies, and the general principle that small irregular moons captured from the asteroid belt are likely to have internal void structures. Its weaknesses are the ones we have been building toward throughout this video. The groove patterns do not fully fit. The Stickney impact survival is hard to explain. The thermal behavior is inconsistent. The orbital characteristics, including Phobos's near-circular equatorial orbit, are unusual for a captured body. Captured asteroids tend to have eccentric, inclined orbits, not the clean equatorial path Phobos travels. Most of the scientific community currently holds this view, but most of them also acknowledge the unresolved issues. The fit is good. It is not perfect. The moderate explanation is that Phobos is a captured body, but with an unusual internal composition. Some researchers have proposed that Phobos may have once contained large amounts of water ice in its interior, which sublimated away over billions of years, leaving behind cavities. Others suggest that Phobos formed from material with a different composition than the asteroids we have visited so far, a class of body we have not yet sampled directly. Still, others propose layered internal structures resulting from previous catastrophic events that fractured but did not destroy the moon. The supporting evidence for this view is the spectroscopic similarity of Phobos's surface to certain primitive asteroid types, combined with the anomalous thermal behavior that suggests internal complexity. The weakness is that it requires a specific formation history we have no direct evidence for. It is plausible, but it is unconfirmed. This is a respected minority view in the scientific community. The bold explanation, and the one gaining quiet traction in recent years, is that Phobos is not a captured asteroid at all. This idea has been around in various forms for decades, but it has gained serious attention since around 2016, when computational simulations began to suggest that Phobos and Deimos may have formed from a giant impact on Mars itself. The story, in this version, goes like this. Early in the solar system's history, a large body, possibly the size of a small dwarf planet, collided with Mars. The impact was catastrophic. It threw enormous amounts of debris into orbit around Mars. Most of that debris fell back to the planet over time. Some of it coalesced into temporary moons that have long since decayed and fallen. And a small fraction of it, in the outer regions of the debris ring, eventually formed into the bodies we now call Phobos and Deimos. In this version of the story, Phobos is not a captured asteroid. It is a fragment of Mars itself, mixed with material from the impactor. It formed in place, around Mars, from debris that was never anywhere else. This explanation has several things going for it. It accounts for the orbital characteristics, including the circular equatorial orbit, which captured asteroids almost never have. It accounts for the survival of Phobos at this orbital distance over billions of years. And it suggests a natural mechanism for the internal void structure, material that coalesced quickly and chaotically from a debris ring, with cavities and irregularities embedded in it from the moment of formation. Its weakness is that the surface composition of Phobos, as measured spectroscopically, does not perfectly match what we would expect from Martian or Martian impact material. It is closer to the dark, primitive composition of certain asteroid types. This mismatch is a real problem for the giant impact theory, and it is the main reason the theory has not yet become the consensus. But here is what is important. The bold theory does not require any exotic physics. It does not require ancient civilizations or hollow shells or anything that violates known science. It just requires us to accept that the simple captured asteroid story we have been telling about Phobos for 150 years may have been wrong. That this body may not be a piece of the asteroid belt at all. That it may be a piece of Mars, formed in place, with an internal structure inherited from one of the most violent events in the planet's history. That is the theory currently rising through the literature. That is the theory that the Japanese MMX mission, when it returns samples from Phobos' surface later this decade, will most directly test. And here, before we leave the theoretical landscape and return to the data, we should pause for a moment. Because there is something worth saying about why this story matters at all. Why are humans so drawn to mysteries about what is inside things we cannot easily open? Phobos has been visible in our telescopes for nearly 150 years. We have known about its existence for longer than most of our great-grandparents have been alive. And yet, the question of what it actually is, what its inside looks like, what its history was, what category it belongs to, has remained open for that entire time. We could have stopped asking. We could have decided, at any point in the last century and a half, that the existing explanations were good enough. That the rubble pile theory, or the captured asteroid theory, or the original simple description from Asaph Hall's notebooks was sufficient. We did not stop asking, and the reason we did not stop asking is that the data kept refusing to settle. Every time someone looked closer, the picture became more complex, not less. Every time someone declared the case closed, a new measurement pried it open again. That is, in a way, the most honest thing science has ever said to us. Not that we have all the answers, not that we know what Phobos is, but that we are willing to keep looking, that we are willing to live with decades of an unresolved measurement and not pretend we have explained it when we have not. The strangest thing about Phobos isn't its density. It's that we have known about its density for more than 60 years, and we still haven't fully explained it. After everything we have seen, the orbital acceleration that started all of this, the lost Phobos 2 mission, the Mars Express confirmation, the grooves, the survival of Stickney crater, the three competing theories, the wider pattern of small body anomalies. The question is no longer whether something strange is happening with Phobos. The question is what that strangeness actually means, and here is where the story takes a turn that most coverage of Phobos has never quite gotten. 2. Because there are aspects of this story that the headlines have consistently missed. There is recent data that has shifted the picture in ways the public conversation has not caught up with. And there is one specific reveal, one fact about Shklovsky and his calculation that recontextualizes the entire history of this puzzle. Remember what we asked at the start of this video. What is actually inside Phobos? Why does every gravity measurement we have ever taken of it return a density that physics says should not be possible for a normal asteroid this close to Mars? Why did a senior Soviet astronomer suggest, in 1959, that this moon was artificial? And why did Western scientists like Carl Sagan engage with the underlying question instead of dismissing it outright? After tracing this story from Iosif Hall's discovery in 1977, through Shklovsky's calculation, through the lost Phobos 2 mission, through the Mars Express confirmation, through the grooves and Stickney crater, and the unresolved gaps in the rubble pile theory, here is what we now know. And just as importantly, here is what we still do not. We know the density, approximately 1.86 grams per cubic centimeter, confirmed by modern instruments, settled. We know that a substantial fraction of the body is empty space, somewhere between roughly 1/4 and nearly half of its interior, depending on what we assume about its composition. That is not in dispute. We strongly suspect that the captured asteroid origin story does not fully explain Phobos. Too many features do not fit. We are still debating between the rubble pile, the unusual composition, and the giant impact origin theories. Each one explains some of the data, none of them explains all of it, and we still do not have a single, complete picture of what specific internal structure produces the void distribution we measure. That is where the science currently sits. And that is where the headlines stop, but the technical literature does not stop there, it keeps going. And the parts that the headlines miss are some of the most interesting parts of this entire story. Here is the strange thing about how Phobos has been covered in popular media. The story tends to come out in two forms. The first form is the breathless version. Mars's moon is hollow, it might be artificial. Soviet scientists thought it was alien. That version takes S.H. Shklovsky's most extreme historical hypothesis, strips out the context, and presents it as if the question is still open in those terms. It is not. The artificial moon hypothesis, in its 1959 form, is not a credible explanation today. The data has moved on. The second form is the dismissive version. Phobos is just a rubble pile. Mystery solved. Move along. That version takes the most conservative current explanation, presents it as settled, and treats anyone still asking questions as someone who has not been reading the recent literature. Both versions are wrong. Both versions miss what the technical papers actually say, because the technical literature, when you read it carefully, says something more interesting than either version. It says that the rubble pile model is the best explanation we currently have, and that it has known mismatches with the data, and that those mismatches have not been resolved, and that the question of what Phobos actually is remains genuinely open in ways that public coverage rarely acknowledges. Let me give you a specific example. The Mars Express papers that confirmed the density and identified the void space used very careful language throughout. They did not declare Phobos a rubble pile. They said the data was consistent with a rubble pile interpretation. There is a difference. Consistent with means the data does not rule out the explanation. It does not mean the explanation is correct. The headlines simplified this into either Phobos is hollow or rubble pile, mystery solved. Neither captured what the papers themselves were saying. Follow-up analyses looked at the gravity field data more carefully. They suggested that the void distribution inside Phobos may not be uniform, that some regions of the moon appear to be denser than others, and that the simulated gravity coefficients fit better when the interior is allowed to be inhomogeneous than when it is forced to be a smoothly mixed pile of rocks. A non-uniformly hollow body suggests something more structured, something that formed through a different process. This finding received almost no public coverage. It sits in the technical literature, available to anyone who looks for it, but it is not part of the public conversation about Phobos. There have also been recurring debates within the scientific community about whether the term rubble pile is being used too loosely in the context of Phobos. Some researchers have argued, in print, that the rubble pile label is functioning as a kind of placeholder, a way of saying we do not have a better category without admitting that the category fits poorly. Other researchers have pushed back against this characterization, arguing that the rubble pile model, while imperfect, is the simplest explanation that fits the most data. This debate is real. It is documented. It plays out in journal papers and at conferences, but it almost never makes it into public coverage of Phobos, because it is a debate about the quality of an explanation rather than about the conclusion itself. And that kind of nuance does not survive the translation into headlines. There is also a quieter question that comes up in the literature. Why has there not been, in all these decades, a focused, dedicated mission specifically designed to settle the interior structure of Phobos? Phobos too tried, it failed. Mars Express did what it could from a distance. The Russian Phobos Grunt sample return mission, attempted in 2011, also failed, stranded in low Earth orbit by a propulsion problem. Various proposed missions have been studied, but until the Japanese MMX mission, there has been no spacecraft built primarily to answer the question Shklovsky asked decades ago. This is unusual. When a measurement anomaly persists for decades, when the same number keeps coming back from independent missions and refuses to fit the existing theories, the natural scientific response is to send a dedicated mission to resolve it. With Phobos, that has not really happened until now. There are reasons for this. Phobos has often been seen as a stepping stone for human Mars exploration, rather than as a primary scientific target in its own right. Mission funding has gone to Mars itself, to Europa, to the outer solar system. Phobos has waited, but it is worth noticing the pattern. The measurement anomaly has been sitting there. The technical community has discussed it, debated it, written about it, and the public conversation, in the meantime, has oscillated between aliens and rubble pile, solved, neither of which captures what the actual scientific position has been all along. The actual scientific position, in plain language, is this. We have a real measurement that does not fully fit our existing models. We have several candidate explanations, none of which work perfectly. We have not yet had the data to settle which explanation is correct. We are working on it. That is the honest version. It is less dramatic than the headlines on either end. It is also more interesting, because it leaves the door open in a way that the simplified versions do not. In the last few years, something has been happening in the scientific literature on Phobos that has not yet broken through into popular coverage. The picture has been shifting, not dramatically, not all at once, but steadily, paper by paper, simulation by simulation. The giant impact origin theory has been gaining ground, and as it has gained ground, several long-standing puzzles about Phobos have started to make more sense, including, in a quiet way, the original density anomaly that started this entire story. Beginning around the mid-2010s, computational simulations of moon formation around Mars began to produce results that were, frankly, surprising. Researchers were trying to model how Phobos and Deimos could have formed from an ancient giant impact on Mars. The kind of impact that, on a much larger scale, is believed to have formed Earth's moon. The simulations had to account for a long list of constraints. The current orbital characteristics of Phobos and Deimos, their sizes, their compositions, as best we understand them, their stability over billions of years. What the simulations found, in study after study, was that a giant impact on Mars could plausibly produce something very much like the Phobos and Deimos we see today. The bodies would form from a debris ring around Mars, in the outer regions of the ring, where material was less likely to fall back to the planet over time. They would have low densities, because they would form from rapidly coalescing fragments with significant cavities embedded in the structure from the moment of formation. They would settle into circular equatorial orbits, matching what we observe. The simulations did not prove the giant impact theory, but they showed that it could work. And that was a significant step, because earlier objections to the theory had been based partly on the assumption that it was difficult to produce moons of the right size and orbit through this mechanism. The simulations weakened those objections. Then came the spectroscopic reanalyses. For decades, the surface composition of Phobos was treated as evidence against any kind of Mars-related origin. Phobos's surface looks dark, primitive, similar in many ways to certain asteroid types, particularly the D-type asteroids found in the outer asteroid belt and beyond. This was treated as strong evidence that Phobos must be a captured asteroid. Why else would it look like one? But more recent analyses have complicated that picture. Several research groups have argued that the surface material we see on Phobos may not be representative of the Moon's bulk composition. The surface may be a layer of dark material, possibly dust accumulated from interplanetary space, possibly material altered by billions of years of solar wind exposure, possibly even Mars dust, kicked up by ancient impacts and captured by Phobos's gravity, that masks the actual composition underneath. If that is true, then the surface spectra of Phobos are not a reliable guide to what the Moon is made of as a whole. This is a significant shift. It means that one of the strongest objections to the giant impact theory, the surface composition mismatch, may be weaker than it appeared. We may have been judging the inside of Phobos by looking at a layer that does not represent the inside at all. The implications are still being worked out, but the trajectory is clear. Each new piece of analysis in recent years has been making the giant impact origin theory more plausible, not less. And that theory has a particular property that is worth pausing on. If Phobos formed from a giant impact on Mars, if it coalesced rapidly from a debris ring, with cavities embedded in its structure from the moment of formation, then the internal void structure we measure today is not a mystery to be explained. It is a signature of the formation process. The voids are there because the Moon did not form gradually, like a planet, with material settling smoothly under gravity. It formed quickly, chaotically, from fragments that came together with imperfect packing, and that have remained imperfectly packed ever since. The empty space, in this view, is exactly what we would expect. The grooves, in this view, may be the result of stress patterns inherited from that violent formation, modified by later impacts and tidal effects. The Stickney impact survival, in this view, is consistent with a body that is not fully solid, but is also not loosely held together. A body with internal coherence inherited from the conditions of its formation, with enough void space to absorb shock without flying apart. This is the most credible explanation that fits the most data. It only emerged in a serious form in recent years, and it is the explanation that the Japanese MMX mission, currently in development, is specifically designed to test. The Japanese MMX mission, short for Martian Moons exploration, is the closest thing we have ever had to a dedicated answer to the Phobos question. It has been in development for over a decade. It has been delayed, refined, delayed again, and rebuilt around updated technology. The mission profile is, in technical terms, ambitious. The spacecraft will not just orbit Phobos, it will land on it. It will operate on the surface for a period of time. It will collect samples, multiple samples, from different locations if possible, and place them in a return container. It will then ascend back into Mars orbit, transfer to a Mars-Earth trajectory, and return to Earth, where the samples will be opened and analyzed by laboratories around the world. This is the kind of mission that does not come along often. Sample return missions are rare, they are expensive, they are technically difficult. The handful of bodies from which we have returned samples, the Moon, a few asteroids, a comet, the solar wind, represents the entire history of human sample return from space. When MMX returns its samples, Phobos will join that list, and what those samples will tell us is not abstract. They will answer specific questions that have been waiting for direct evidence for decades. Question 1. Is the surface material of Phobos chemically and isotopically similar to Martian crust, or is it similar to primitive asteroid material? This is the most direct test of the giant impact origin theory. If the samples look like Mars, the theory will be strongly supported. If they look like the asteroid belt, the captured asteroid theory will gain new life. Question 2. What is the actual internal structure beneath the surface? MMX will conduct gravity mapping at much higher resolution than Mars Express was able to. This will not, by itself, answer every question about the interior, but it will produce a far more detailed map of how mass is distributed inside Phobos than anything we currently have. It will tell us whether the void distribution is uniform or non-uniform. It will tell us whether there are large cavities, networks of smaller voids, or some combination. It will give us, for the first time, a real picture of what is inside. Question 3. What are the grooves actually made of? The mission will examine surface features, including some grooves, at close range. We may finally get direct evidence of how those features formed. The implications go beyond Phobos itself. Phobos has been proposed, more than once, as a potential staging base for human Mars missions. The argument is straightforward. Phobos is close to Mars. It has very low gravity, which means that landing on it and launching from it requires very little fuel. It would, in principle, be much cheaper to send astronauts to Phobos than to the Martian surface itself. From Phobos, those astronauts could remotely operate equipment on Mars, conduct scientific observations, and serve as a kind of orbital base camp for surface missions. If MMX confirms that Phobos has significant internal cavities, that is not just a scientific finding. That is engineering data. Internal cavities could provide natural radiation shielding for crewed missions. They could offer thermal stability. The interior of a body that size would experience much smaller temperature swings than the surface. They could even, in some long-term scenarios, be developed into habitats. This is a serious area of study within space agencies. It is not science fiction. The internal structure of Phobos is directly relevant to the future of human spaceflight in ways that the public conversation has rarely emphasized. There is also the wider scientific lesson. Phobos has been teaching us, slowly and patiently, that small bodies in the solar system are more diverse than our simple categories suggested. The neat division between captured asteroid and primitive remnant and rubble pile has been breaking down for years. Each new mission to a small body, Bennu, Itokawa, Ryugu, 67P, has revealed unexpected complexity. Phobos has been part of that pattern for longer than any of those bodies, and its mysteries have been open for longer. When MMX returns its samples, we will not just have answered the Phobos question. We will have refined our entire framework for thinking about small bodies. We will have a better sense of how moons and asteroids and comets and the wreckage of ancient impacts can blur into each other. We will have, in other words, a more accurate picture of the solar system we live in. That is what good science does. It does not just answer questions, it changes how we ask them. And here is what makes all of this truly remarkable. Iosif Shklovsky was, in a strange and quiet way, partly right, not about the part everyone remembers, not about the artificial origin. He was wrong about that. The hollow moon hypothesis, in its 1959 form, a manufactured object placed in orbit by some unknown intelligence, has not survived the data. It is not where the scientific evidence has led. The samples MMX returns will almost certainly confirm a natural origin, whether that origin turns out to be a captured asteroid or a fragment of Mars from an ancient giant impact. But he was right about something deeper. He was right that the density of Phobos, even by the standards of his time, was so anomalous that the standard explanations available in 1959 could not account for it. He was right about the underlying calculation. He was right that the orbital tracking data, which everyone else was trying to explain away through small adjustments to existing models, was telling them something the existing models could not absorb. And he was right that the answer, when it eventually came, would require us to revise our understanding of what Phobos is. He was right about that too. It just took us decades to find a natural explanation that fit the math he saw clearly. The artificial moon idea was not a wild guess. It was the only option left when the rest had been ruled out, and it stood as a placeholder for an entire scientific question, holding the door open until better data arrived. S.H. Shklovsky was not asserting that aliens had built Phobos, even if his most famous sentence has been read that way ever since. He was asserting that the existing explanations had failed, and that something unusual was needed to account for the data. The artificial origin was the most extreme form of something unusual that he could state clearly. The unusual thing turned out to be different from what he proposed, but the unusual thing was real. Let that sit for a moment. The most controversial scientific suggestion of the 20th century about a moon was wrong in its conclusion, but the measurement that drove it was right all along. And the right answer, when it finally emerged, came not from rejecting his data, but from finding a natural explanation as strange as the one he proposed. A moon that may be a fragment of Mars itself, formed in a violent collision 4.5 billion years ago, carrying inside it the cavities and irregularities of that formation, orbiting the planet that may have once been part of itself. That is not less strange than what S.H. Shklovsky imagined. It is differently strange, and in some ways, it is stranger, because it is real. But there is one more piece of this story we have not touched. Because Phobos is not the only moon in our solar system whose density does not add up. There is another one, much further out, much stranger in its behavior, with a density even lower than Phobos, and a surface that looks like nothing else humans have ever observed. A surface so unusual that scientists themselves struggle to describe it without reaching for analogies that do not quite work. Some researchers quietly call it the sponge moon. What we know about it makes Phobos look almost ordinary. And what we do not know about it is a question we have been ignoring in plain sight for decades. That is a story for next time. Tonight, we did not just learn about a strange moon orbiting Mars. We watched what happens when reality refuses to fit our models. We saw a Soviet astronomer working alone with a stack of orbital data write down a sentence that the entire scientific community would spend the next 65 years trying to explain. He was not trying to make headlines. He was not trying to be famous. He was trying to honestly describe what the numbers in front of him were saying. We watched a spacecraft fall silent in 1989, in its final hours before it would have answered the question S.H. Shklovsky had asked 30 years earlier. Phobos, too, carried with it not just instruments, but the hopes of an entire generation of Soviet scientists. It returned data that strengthened the puzzle, and then it disappeared, with its closest measurements forever beyond reach. We watched a European probe in 2010 confirm what the rubble pile theory could only partially explain. Mars Express did not solve the mystery. It made the mystery undeniable, and we watched, slowly, a different kind of answer begin to emerge, not from rejecting the original data, not from explaining it away, but from finally finding a natural mechanism in giant impact simulations and updated formation models that could account for what had been sitting in the literature since the middle of the last century. This was not a story about a hollow moon. This was a story about how long science is willing to wait, and yet, even now, the case is not fully closed. We do not know, with certainty, whether Phobos was captured or formed in place. The giant impact theory is gaining ground. The captured asteroid theory is not yet defeated. The samples MMX returns will likely settle this within the next several years. But until those samples are in laboratories on Earth, the question is technically still open. We have not yet mapped the internal void structure of Phobos at high resolution. We know the body is roughly 30% empty, give or take. We do not know exactly how that empty space is distributed. We do not have a single, complete explanation for the grooves. Three theories compete. None fully wins. And the thermal anomalies first detected by Phobos 2 have never been fully reconciled with any current model. They sit in the data, waiting. But here is the thing. Every one of these gaps is a question that the next mission is specifically designed to answer. The mystery is not permanent, it is current. And we are alive at the precise moment in scientific history when these questions are being settled, not by speculation, but by direct measurement. That is a rare thing. It is worth noticing. There are a few things worth taking from this story that go beyond Phobos itself. The first is that small details carry enormous implications. A fraction of a gram per cubic centimeter, a number so small that most people would dismiss it as a rounding error, has been forcing science to reconsider what a moon can be for more than 60 years. The universe does not announce its mysteries with fanfare, it hides them in decimal places. The job of science is to take those decimal places seriously, even when they are inconvenient. The second is that mysteries are powerful precisely because they expose hidden assumptions. Phobos forced us to question what captured asteroid even means. It made us realize that we had been using a category, small, irregular, rocky moon, without ever testing whether the things in that category actually belonged together. The mystery was not in the moon, the mystery was in our own framework, and Phobos was just the body that revealed it. The third is that science grows stronger through uncertainty, not despite it. The hollow moon question stayed alive longer than most scientific questions. It was not closed prematurely. It was not declared solved when it was not. And science is better today for having held that question open for so long. The fourth is that one strange object can become a question about entire systems. We started with one moon. We ended up rethinking moon formation, asteroid capture, planetary impact dynamics, and the structure of small bodies across the solar system. Nothing in the universe sits in isolation. And the fifth is this. The deeper we look, the more complex reality becomes. That complexity is not a flaw in our knowledge. It is the texture of being alive in a universe that has not yet finished revealing itself. So I want to leave you with a few questions tonight. What makes a discovery important? The object itself, or the questions it forces us to ask for decades afterward? Phobos has not been particularly useful, in any practical sense, for more than a century. But it has been one of the most patient teachers in our solar system. How often do we accept an explanation simply because it is familiar, even when the data has quietly stopped fitting? How many other anomalies are sitting in scientific papers right now, waiting for someone to take them seriously? What does it say about science that the most controversial guess of the 20th century turned out to be partly right, in a way no one could have predicted? And what does it say about us, about humans, that we keep asking these questions, even when the answers take generations to arrive? Sit with those for a moment. They are bigger than Phobos. If this story pulled you in, tell me in the comments which part stayed with you the most. Was it S.H. Shklovsky's calculation, alone in his Moscow office? Was it the lost final transmission of Phobos 2, just before it would have reached the surface? Was it the moment Mars Express confirmed the impossible density in 2010? Or was it the realization, at the very end, that the man everyone called wrong was the one who had been seeing the data most clearly all along? I want to know. And if you want more deep space mysteries told this way, slowly, carefully, with the science intact and the wonder preserved, subscribe to Galaxy Pulse. We go beyond the headlines, every single time. I will see you in the next one. The moon was strange, but what it revealed about how long we can be partly right and partly wrong at the same time, that may be stranger still. Phobos is still up there, still orbiting, still hollow, in its own quiet way. and still waiting for us to finish the question it asked. Decades ago, in a notebook in Moscow, when one man underlined a single sentence and put down his pencil,